Okay, well, good evening, good afternoon, good morning, depending on which part of the world you're calling in from or listening from. Welcome to Think Tech's virtual meetup summer season. I gather this is one of the last sessions of what's been a very successful season of virtual events. This initiative is organized by the Saudi Ministry of Communications and Information Technology, and the think tank, or the aim of the think tank's season of these virtual meetups is to stimulate a whole range of different ideas and thought process digital environment, and to spread digital awareness and to get us all involved and to get us talking about digital. Today's session, we're going to be talking about the future of quantum computing, and it's an area that's growing in a lot of, getting a lot of attention and growing in lots of different areas. And we've got an amazing set of panelists and guests here that we're going to have some fun with and see what makes them tick. So to begin with, my name is Nick Ayton, and I'm moderating this session. And my background is technology or computer science in the 1970s. I came across quantum computing several years ago, and I've been following its progress. So I'm an evangelist, a keen supporter of what is going to be a profound few years ahead of us as this technology gets a grip and takes shape. My background is as a serial technologist, tech entrepreneur. I've had several startups, I've worked for cities, and at the moment I currently help founders and businesses raise capital from a number of different areas, funds, tech funds, family offices, sovereign wealth funds, and so on. And my hobby is actually making a film or writing a screenplay to make a film about the existential threat of artificial intelligence. So there you go. I'm involved in lots of different things, but let's crack on. And so I'm going to get the panelists to give you a sense of where they're coming from, but I want them to do it in a slightly different way, which is to talk about their journey to this point and how they came across quantum computing. So we'll start ladies first. Reena, maybe you can give people an introduction and how you came to stumble across quantum computing.
Yeah, thank you. I think that's a much more interesting way to introduce. Yeah, good morning, good afternoon, and good evening, everyone. I'm Reena Dayal, and I have been in the industry for around 27 years. And I don't want to give you the history of that, but let me talk a little bit about my passion for physics. So, when I was growing up, I wanted to do advanced physics. And I come from a family of engineers who believed that physics was too theoretical, right? So I ended up getting influenced in doing engineering, but I continued to read physics, as a hobby, right? So I would read about string theory, most of the popular stuff, not go deep into the mathematics. Learned about quantum computing, particle theory, and so on. And my friends would tell me, why are you wasting your time on this? Are you planning to do more advanced physics in the future? I'm like, not really. Said, so why do you read this stuff? I said, I just like it. So I read it just like every other book that I read, right? And then as I was in Microsoft announced the Quantum Development Kit in early 2018. And I was like, let me see what I can do about this. So at that point in time, we'd announced the kit, and it had become available for people to start, using the kit, use the quantum programming language called Q#, and start programming with it. So as I started toying around with it, I realized that if you're not from the quantum computing physics background, then it's very difficult initially for anybody else to actually pick up the concept of quantum computing and start programming using that. And the reason is that, computing is an abstraction. Computing is an abstraction on certain physical aspects that we understand, right? So anyway, I'll talk a little bit more about this later, but I made a certain discovery based on this, and I got passionate about it, got in touch with the quantum computing team in Redmond. I also am the chairperson of the Quantum Special Interest Group as part of Institute of Electrical and Electronics Engineers. So I'm doing that. I'm associated with the Quantum Initiative that IEEE has. And yeah, we'll talk more about that. So that's the history.
Well, interesting. So Simone, you're a prolific writer of a few things on quantum, which we've come across. So tell the audience, what you've been up to and how you came across quantum.
Yeah, and thank you very much for the question. Now, I mean, my first time with quantum computing, I was a computer science engineer to be, right? I was studying in the university on my computer science courses. At that time, I had my first company, which I exited quite a while ago. And after that, I was starting doing angel investing. So my second time with quantum was about understanding what I could do with companies which are actually investigating what quantum is. Now, fast forward to what I'm doing now. I'm an equity partner in PwC, and basically I'm responsible for what we call digital infrastructure, which is, whatever is around quantum, but also whatever is around AI. And we will talk about the mix of these two things in a bit. But in general, basically, the most of my time in the region has been dedicated to create use cases and way to use technologies which are extremely valuable, but they need to be applied to some kind of industry or some kind of process. And that's the last thing about me and quantum computing, which is what I'm doing today. And as you know, I've been focusing on the Middle East and North Africa for a while, which is a very interesting area in which quantum computing has a lot to give. And we will talk about that in a bit.
Okay. Fantastic. Jean-Gabriel, we spoke a few weeks ago, you may or may not remember.
Yes, I do.
So, so we didn't touch upon how you came involved in quantum. So, what's your story?
So, hi, everyone. I'm working at Quantum Nation, the first VC fund dedicated to quantum technologies. Previously, I was working in a private equity fund focusing on deep technologies. And one day I had the opportunity to discuss with Christophe Jurzac, who was a PhD in quantum physics and also one of partner in charge of Quantum Nation. And he was telling me about the story of this VC fund focusing on quantum technologies. And at this stage, I was working on a hydrogen station and how hydrogen can be disrupting the energy sector. And one of the major drawbacks was due to the properties of the liquid hydrogen and the storage of it. And all this kind of problematics could be answered by quantum computing by unlocking some fundamental science problems and helping researchers to develop new materials and better understand how the universe work. So that was a great discussion, and it's an amazing journey to help develop such technologies and see the potential application of them.
Fantastic. So look, we're in at the beginning. I mean, I've in my last 45 years in the technology industry, I've seen different technology waves come and go. So I started in mainframes, and then there was the personal computer revolution, and then there was the internet revolution. So we're now moving forward into the quantum realms, quantum information sciences. It's all starting to happen. But obviously with most new waves or new evolutions of technology, we need some fundamentals in place, don't we, to take us forward. So I'd like to get a sense, I mean, Simone, you crack off with this one, but I'd like to get a sense of where do you think we are, because to get quantum going, we need lots of different moving parts and we need some fundamentals in place. So where do you think we are?
Yeah, I mean, look, there are different versions of where we are, right? Because the reality is that quantum computing is not democratized enough. In a way, I mean, big governments and big tech companies have been experimenting with this for a while, and they are way more advanced than anyone else. Now, the reality is we're not at the point in which we can claim quantum supremacy, although there has been some claims by Google in the last couple of years, them being relatively close to demonstrating that, at least for some algorithms. I mean, the reality is we have some quantum computers which are working as of today. We have little which has been done to prove the fundamentals of the theory for supremacy as of today. And again, there is little transparency about what different governments have been experimenting with. But I mean, I would say we are reasonably sure that the major governments, I mean, the major superpowers in the world have been reaching some decent level of research in this, which is still far away from having a practical application, at least for the use cases we'll discuss in a bit.
So we get to a point, don't we, where we need hardware, we need software, we need computer languages, we need compilers, we need this whole stack. So Reena, where do you what's your feeling of level of maturity? Are we getting there? Where are we, do you think?
So I think, I sort of agree with Simon that there are different versions of where we are. So let's examine, and you rightly talked about the stack. I think it's very important to consider the stack in totality. There are multiple hardware-based approaches that are being tried out today. Some of them at, close to 0 degree Kelvin, and some of them at room temperatures, right? And there are different technologies that people are betting on when it comes to the scalable quantum computer that we really want. The issue is with error correction, right? There's a lot of lack of cohesion that happens in the quantum calculations that are being done, and what happens is there's a lot of error correction that needs to be done, which is preventing people from creating a truly scalable quantum computer today. If you want to scale to 1,000 qubits, can you do it? No. So that's where the progress is now waiting for some basic new breakthroughs to happen so that we can reach to the next step. When it comes to the rest of the stack, I think there are multiple companies right now who have stacks which allow for multiple hardware sitting at the bottom, and then you can have a programming language on top of that, and you can start working with quantum algorithms on classical computers or in a limited way on those quantum hardwares that are existing, which could be 5 qubit, 10 qubit, depending on the hardware that we're talking about. Or and when I'm talking about qubits, I'm talking about physical qubits, because of error correction, the translation to the software qubit is also like there's a big ratio involved. So while we are far away from this whole concept of the truly scalable quantum computer, there are a lot of, we understand as an industry, as the government, that, what the stack is going to look like. There are elements of the stack that are in place. And more importantly, there are aspects of quantum computing algorithms that can today be run on classical hardware to solve some of the more difficult optimization problems, which could not be solved yesterday. So this is not really running quantum algorithms on quantum computers, but quantum algorithms adapted and modified to be used on classical hardware. And they are able to now solve problems which were not solvable earlier. So if you look at this aspect of quantum-inspired optimization, I think we're making a lot of progress as an industry, as the industry. Right?
I'm pretty sure we'll touch on some of that stuff. I mean, Jean-Gabriel, when we last spoke, I mean, it's not just pure quantum computing. It's a vast spectrum of quantum information sciences that touches different aspects. How do you see the maturity of where we are? Because you're talking to a lot of different founders and projects. And
yes, well, just
and a large variety of different use cases.
Yes, totally. So just to add things to what Reena said, that we currently are able to perform interesting computations on noisy qubits. So there are quantum computer based on noisy qubits, leveraging other kind of algorithms, such as variational ones, who are resistant to errors. And those are able to offer specific application and do things that classical computers are not able to do, especially in fundamental science. And research groups are leveraging this kind of special purpose hardware to find an answer to very, very complex problems. And also, we are able on the part of leveraging quantum algorithms on classical computers. We talk about quantum-inspired methodologies. And we have a startup in portfolio developing quantum-inspired algorithm for optimization problem in the financial industry. And they are able to already prove some speed-ups on selected problems For instance, detecting fraudulent transaction in a large set of transactions, and way better than what their classical model are currently doing. And on the side of quantonation, we are seeing quantum technologies as a large scope with quantum sensing and quantum communication, which are way more mature fields. Startups are already developing some commercial products. Some are even generating revenues. And on the quantum computing side, we see that there are a lot of hardware with different maturities, but also with different purposes. And so short-term hardware will be first mover in the field and able to lock commercial customers with dedicated applications. And then in the longer run, some technologies are able to offer a speed up way more broad than the short-term technologies. And those kind of players will still have to be in front of the players that locked some commercial customers. So it will be hard in the long run also to just pop on the market and try to move out historical players. And there's a lot of different approaches, but what we see right now is there is still the possibility to have a product-driven approach and develop use cases with selected industries and be able to offer them some quantum speed up, even if the hardware is still not perfect and still not the fault-tolerant, scalable quantum computer as we theoretically know.
Okay, that's very interesting, isn't it? Because our hope, is that we can actually get this technology stable as soon as possible, because we can start then solving some of humanity's most tricky problems. We can start thinking about, the next evolution of civilization in a sense. The way I look at it quite often is we had steam power, which was a wealth creation revolution, number one, and then we had electricity, then we had transistorization, and we're now at that sort of quantum AI juncture, where this could actually be the beginning of the next wealth creation opportunity. So with that context in mind, Simone, let's start talking about certain specifics around industries and sectors what do you think this technology holds, and where is the promise in some of these sectors from your point of view?
Yeah. Look, I think, as you said, the long-term promise is basically with AI, right? That's a mix of technologies which seem like the infrastructure and the brain, put together. And basically that's something that will definitely give us a chance to do simulation at the light speed and give us a chance to perform decision-making at a level which was unprecedented in real time or close to real time because of the computational possibilities. Now, these things will apply to many different industries. Basically, the first thing that I can think about is financial services. I mean, in financial services, there is a lot of decision-making that needs to happen based on fundamentals and needs to be applied very fast. Now, the mix of AI and a technology like quantum computing may actually do the last step in bringing people far away from the market, while basically a market can be completely robotized and automatized, right? Which is basically something that could create very interesting scenarios and definitely revolutionize the whole industry of financial services in terms of market access and in terms of speed of market decision making. The second part of the story, which I think is extremely relevant here in the Middle East and North Africa, is basically the application of whatever is natural resources. So basically all the problems of optimization, from drilling, from identifying new oil fields, from simulation of what happens if you basically start using explosives in different areas of the oil fields, it's something that could be revolutionized by quantum computing and AI. Now, there are some of if you look at the most notable usage of quantum computing, at least at the experimental level in the region, they are mostly all in the oil and gas sector, which gives us a hint that there is quite a lot to be done there. The second part of the story is in manufacturing to core. Now oil and gas is one part of the story, but if you think about petrochems, especially if you think about high-value petrochems, like polymers or basically whatever you would use for the next generation of materials. Now, the advantage that quantum computing with AI can bring you is a simulation at the molecular level, which is at unprecedented speed that can actually enable you to do the full testing in a simulation instead of doing that in the real world. On the other side, you have a huge potential for optimization. I mean, as a full disclosure, I'm an investor in optimization companies for petrochemicals, and there is a lot that we are trying to do in basically applying quantum computing to that level of optimization. And I think as a last point, or as a last 2 points, basically defense, it's something that may be completely revolutionized by the application of quantum computing. I mean, think about in-the-field decision-making and everything that can be around autonomous weapons, both in the loop and out of the loop. Now, probably this is a topic for a completely different webinar, but that's something that has a huge potential, especially for a region like this, in which there is very little people to have in the army, right? Because the local people in many of the countries are limited. So the reality is that you can basically revolutionize the army by having a robotized army. And finally, I mean, just as a final thought, is basically whatever is around robotics and automation of compliance. I mean, again, in a region in which a lot of the money is going into remittances, the possibility to automate by using AI and quantum computing can be massive. And I will stop it.
Yeah, look, I think, it's got there's a lot of opportunity here. So, Reena, where, I guess, hopes and dreams, where do you think, the quantum computing and this technology is going to start having massive impact in the sectors from your point of view?
I think I agree with the sectors that Simon talked about in terms of the financial sector and wherever there is any, wherever you have to study molecules, right? And he took the example of, petrochemicals, I think, right? Now, I would like to extend that and say, this whole concept of trying to revolutionize the energy sector by trying to mimic nature. I think that's possible when you have the power of quantum computing in your hands. If you look at how fertilizers are prepared by nature, right? There's very little energy that goes into it. There is no byproduct that is harmful for the environment, and it's all a natural cycle. Now, being able to examine stuff deeply at a molecular level at remarkable speeds will allow us to be able to understand how many of these processes are working and how we can mimic them rather than create fertilizers the way that we are doing today, which actually uses up a lot of energy. And these are synthetic fertilizers, they harm the environment and so on and so forth. Same is true for pesticides and so on. So I think there is a whole opportunity in creating clean energy, great solutions for humanity. That's one. The second area which is getting impacted even today is in the healthcare sector, right? I mean, if you look at if you look at healthcare and you look at medical devices, for example, there is a lot of opportunity to optimize some of the existing processes. And a good example is a use case which was done in the United States for reducing the time and increasing the efficiency of an MRI scan, right? Because we all know that, if you dig deeper into how MRI scans happen, they are not an exact science, right? It's an optimization problem in a sense that a lot of images are taken, the intensity at which, the measurement is set, that is also done based on some prior knowledge of how things work, right? Like the person who actually does the setting is a specialist. And then, the doctor actually does a little bit of a heuristic evaluation based on past experience. So what happens is the more experienced the doctor, the more the chances of him or her being able to actually detect a tumor, for example, at an early stage. But, using a combination of AI and, quantum optimized, you can start detecting tumors much earlier so that they can be, patients can be treated at an early stage, thus ensuring, better quality of life, longer lifespans, and so on. So I think that's another great area, which is where quantum can be very impactful. The third thing that I want to talk about is a little independent of individual areas. Today, as scientists or as people who are technologists, we look at 3 or 4 very different problems in this world, which are considered to be close to, they're non-solvable today. One is the human lifespan. It's a limited lifespan, right? You age and you die. The second is faster than light travel. You can go to space, but you can go only so far, right? The third is how does an understanding of how the human brain works. We understand very little of how the human brain works. And it's one of the most advanced computers that we are aware of, which works at very little energy, uses a very small amount of energy. And it does remarkable calculations at very, very advanced speeds, right? But we don't know how it works. And then, of course, there is this desire for having a scalable computer, which goes beyond Moore's law, right? Because Moore's law has reached an end. And quantum is one of the promising areas which is showing us the possibility of probably getting to that computer. The thing with all of these problem statements that I've talked about is that if you solve one of them, you have the capacity to solve all the others.
Sure.
So, yeah, because if you increase the lifespan of human beings, then the knowledge retains longer with the human. And instead of doing research for 20 years, you do research for 80 years or 100 years, and then you actually solve more problems. If you get quantum computing, like a scalable quantum computer, and you can get the massive parallelism that comes with it, you can now mimic the human brain. The moment you can mimic the human brain, you can solve the other problems, right?
Oh, look, we want to get into some of that sort of the future stuff in a second. I mean, John Gabriel, I mean, you're again, you're touching a lot of aspects of this field. I mean, where are the big moves in these sectors going on? I mean, we've talked about chemicals and polymers, we've touched on healthcare, we've touched on financial services. I mean, I guess, how do you see it? Where's the excitement? Where are we going to see some impact in these sectors?
Well, just to emphasize what Reena and Simone just said, there is a Boston Consulting Group who unveiled a study about how quantum will help to fight climate change. And they introduce many aspects in which, like, quantum computing will at some point be able to solve humanity's most challenging issues. So that said, we also know that in the future we'll really need that kind of tools. In the short term, as I was saying, it will really help to unlock some value in the science area. And by unlocking this knowledge, we'll be able to better understand how chemicals work, as Reena said, and give the keys to researchers to go way beyond what we currently know. So we have identified today very precise industrial applications that will revolutionize some industries, in the financial services, in the chemicals, in the pharmaceutical industries. But the best is yet to come. And we really believe that giving these keys to researchers will help to better understand things that will give rise to applications that we yet are not able to see. So we know where the value is in quantum computing, thanks to the acceleration allowed in these industries. But what we also do not know yet, and what will be the massive revolution, is how the quantum computers will help us understand the world we live in. And there are so many things we do not understand right now in the physics and the biology side, that quantum computers, that research in quantum computing will really help unlock this value, and is a major asset of the next development. And that's what we believe in. And still there is interesting application, but a lot more is going to come also.
Yeah, I think that's a fair comment. I think all three of you have sort of summarized it beautifully in terms of the direction of travel. The so-called hard problems, humanity and for civilization, how do we live longer, and how do we cure diseases, how do we feed 10 billion people, how do we stop the planet heating up? I mean, these are all within the realms that we're all passionate about, because we hope that this technology matures and stabilizes quickly, and that needs to happen. In a sense, we're sort of in a there's lots of different directions, there's lots of different flavors of quantum, there's lots of different people trying to sort of break new ground, but we need some stability, and we need to start creating some standards. And just before we came on air here, we had a quick chat with Reena about some of the things that need to happen to help us get to this level of maturity. And one of them, of course, is people and skills and access to the right people, because we can't just lean on academia all the time and researchers. So give us your thoughts, Reena, on sort of some of the things that need to happen in background, because it's all about people ultimately, and you may not have enough of the right people in the right places. What's your thoughts?
Yeah, sure. So I think deep and fundamental research in physics, quantum physics, will continue to be done by the people from the physics background. But as we move towards computing, we are now talking about quantum information science, and we're also talking about computer science. And the reality is that when you start working on some of these optimization problems that all of us talked about, you're actually doing programming using quantum algorithms, but you will also be doing, you will always have a classical computer also running, you'll have both the stacks running together. Why? Because you don't want to use a quantum computer to add a 4 plus 4 plus 8, right? Because you will get an approximation. Quantum computing is all about probabilities. So that a classical computer is good for those things, and therefore you will always have a combination. Now the question is, do you take a computer science person and convert them into a quantum programmer, or do you take a quantum physicist and convert them into a quantum programmer, right? And that's one question. When you examine that question, you realize that there are a lot more computer programmers out there than there are physicists, right? So if you want to scale up the workforce for quantum computing, we need to find a way to easily train people from being computer engineers, classical computer engineers, to quantum computer engineers. And when I talked about that little story of my getting involved in quantum, that's the first thing that I started in India, was to I started it first within Microsoft India. I got a set of computer scientists and programmers together and said, hey, let's start studying this subject and see how we can program. And the interesting thing is that you have to unlearn classical computing to understand quantum, start programming in quantum. It's not like, hey, I learned C# and I can now learn Q#. It doesn't work like that. Yeah. So it's an interesting journey. Over a period of time, we've tried to, now, we're also building the ecosystem in India and doing this training with educational institutes. I'm driving it through IEEE, making sessions available to other people. So there's a need to make the curriculum much more understandable for a computer engineer, so that they can become quantum engineers. So I think that's the approach I think that we need to take. We also look at people from the physics background to start doing more computer science courses and see how they would be interested in doing deeper research in this topic on quantum information science and computing, right? So I think it's a mix and match. It's a multidisciplinary field. If you look at sensing, which Gabriel talked about, right? I think that's that's at the hardware level. There are people who are from a sensors background getting into quantum computing. Quantum communication, people from a photonics background are actually getting into quantum communications. So, a lot of this is like a churn happening in all these multiple disciplines right now to create more sense of what is going to emerge. So it's the right time to do workforce development. All governments should be focusing on workforce development at this point in time. That's my view.
Makes sense. I mean, look, I do, that's really good observation. I think also, I'm going to ask Simone this really, but I don't think people realize how hard quantum computing is, how hard and difficult it is to program these things, to even get some sense out of it. what do you think, Simone, about the regional players? You're in the Middle East. I mean, what do the regions, what do the countries, what needs to be done at a fundamental level to help us get more traction in quantum computing, do you think?
And that's a very fair question, and with a very difficult answer, right?
Cool.
No, I mean, jokes apart, the reality is that the Middle East historically has been a consumer of technology which has been developed outside of the region. I mean, as of today, if you look at how many of the things we commonly use in terms of hardware and software, which are created or are even partially developed in the Middle East, that's a very small minority of what it is. So the reality is that what the Middle East should start doing is, on one side, investing in talent, as we were just discussing about. Now, this talent, of course, means, programming, quantum computing. We all understand that it is a very different programming. We all understand it's a very complicated new approach to computing. Now, I would say my line of thought in this is that whatever we discuss as complicated and different is a mix of two things, and this applies to many technologies. The first one is it's different, right? And we are all used to programming and things which have been around for a while. I mean, even if you look at the most advanced, object-oriented programming language, which is large-scale use, is not very different from what was basically around in the 70s. Of course, there is a new paradigm, but there is a base which has been established for a while. The second part of the story is that the interface, basically the language as an interface, didn't develop enough yet. So basically, we are still far away from having users of quantum computing. Basically, what we have is programmers, and as I said, with a very complex interface, but we also need to develop users, right? Well, users means people who are able to understand what are the advantages of this technology and how this could be managed to provide a business outcome. And this is probably the trickiest part of where the MENA region is supposed to invest. Now, the other part of the story could be financing the development of infrastructure. And I keep referring to the term infrastructure because, again, if you think about network technology, we all use it, right? Do we know how to program a router? Not really. Do we know how to configure a router? Not really. But we are all using that. Now, what I foresee is a moment in which quantum computing is at that level of simplicity, is at that level of large-scale usage. Maybe not the level of network, but it will be at the level of a business user to basically work with it. And as a last thought on this, as I said, this is to be taught as an infrastructure. And if the governments in the region want to make this infrastructure available, that's the moment in which they should start investing in understanding how to make that available. Especially in small countries, it will be important for governments to have an active role because none of the companies which is around will have an interest to basically invest in this and provide that to the general public. And this thing can be the next big accelerator in creating a full ecosystem of startups in the region.
Yeah, I think that's fair and valid. So let's build on that and talk about other means of doing this. So if you look at sort of Google and IBM and Honeywell, some of the big manufacturers, Rigetti even, they're starting to drop machines into different geographies. IBM dropped a machine into Japan, into Germany. They've got about 35 machines now deployed, and they're just selling their time and access. So in a sense, is that one of the models? So, Jean Gabriel, we've got an opportunity here to, within countries, to actually give teams of entrepreneurs and pioneers in this area and young physicists access to machine time, and then to curate and incubate, ideas and products and services around that. Do you think that's a viable model that countries should be looking at?
Yes, there is one thing that Simone forgot is that the government should also fuel the innovation, and that can be through academics, that can be through VC fund or incubators. So we need to help startup be in contact with the users, as Simone said. And in fact, the user are high-performance computing centers or industrial ones, building on-premise HPCs, integrating quantum technology in them, or helping the cloud players, like the American ones, integrate those kind of technologies. And that's what Google, IBM, Amazon are doing currently, even Microsoft with the Azure suite. And those must be offered to startups that are willing to develop some quantum technologies. But also, there is a sovereignty issue. And we believe that each country willing to have its own independence and its computing aspect should fuel this innovation and be able to be independent on those technologies, because at some point the provider will be the hardware manufacturer and they're able to reach the whole world with the cloud solution. But if you want to keep your data secret, there is a lot of things which is done on the blind computing side with quantum computers not able to interact with the data they are processed in, but it's really long term. And in the end, you need to have your own quantum computer to be able to process your defense computation on it. And that's a key thing, meaning that you should fuel the innovation in your country or in your region to be able to be competitive, but you should also finance your own needs of computation. So there is two sides of it. And I believe that right now the field is really boiling and not mature. Not as mature as in the US, and it's still the moment to invest because the technologies developed by IBM, Google, or Microsoft are based on ion-trapped or superconducting qubits, but there is also other hardware which in the long run will be able to offer very interesting speedups, or also in the short term. For instance, we invested in a company developing quantum computer based off neutral atoms. And this is a very interesting technologies in the short term. And we also invested in technologies in photonics-based quantum computing, which in the longer run can provide some error-tolerant computation. So there is different hardware offering different promises, but in the end, if you are government and you want to perform confidential data on it, you need to have your own hardware and therefore fuel this kind of innovation. Either through incubator or VC fund, because VC, we are a platform between the academic world or the innovation developed by entrepreneurs or ex-researchers, and we're able to help them scale. And we're the one taking the risk of the technology which doesn't work. And in the end, we are jointly taking this risk with government, thanks to public support, but government cannot substitute in front of VC fund in the same way as VC fund cannot substitute in front of government. And that's a joint work. And I believe that in the end, my conclusion would be that government should fuel the innovation in the academics and also in the financial mechanisms.
Yeah, I think that's really excellent points you make there. And so I want to sort of go a bit more blue sky now. I mean, Reena was itching to sort of talk about the future and what have you. But let's roll forward, 10 years. And I'm one of these people that think 10 years is a very, very long time, especially the rate of the accelerated learning of artificial intelligence and some of the advancements we're making. So let's go a bit crazy, Reena. Where do you think we're going to be in 10 years' time? Where's quantum computing going to be? Does it mean that RSA encryption is completely busted and we need new post-quantum cryptography? What's the world going to look, a quantum world going to look like in 10 years' time?
So I agree with you. 10 years is a really long time from a technology acceleration standpoint. And this is purely my views, not representing anybody. If you just ask me where quantum computing will be 10 years from now, I will tell you that we will have at least some aspects of the quantum internet in place. It'll be like the early internet, not even early. All the major countries will have some aspects of the quantum internet 10 years from now. We will have made a lot more progress on the number of qubits from a quantum computing perspective. And we would have definitely moved beyond quantum optimization on classical, and we would be doing computations on an actual quantum computer 10 years from now. And as I'm speaking this, I'm actually terribly aware of the fact that I'm probably underplaying it, right? It's going to be much more than that. But let me be a little bit more restrained. I will just stop at this, that we will have the quantum internet in some form at that point in time. And there will be a quantum computer blueprint, which will be, sort of, becoming or have become the de facto standard worldwide. And yeah, we will be trying to solve some of the biggest problems.
So I get that standards is something that we'll probably thrash out over the next 3 to 5, maybe 6 years. But do you think that we'll be using, computing in anger, so to speak, to actually solve things in, some of these problems? Or do you think we're still going to be standing on the sideline?
We will not be on the sideline.
For it to mature even more. Are we gonna solve Alzheimer's, for example? With the flat protein. Are we gonna get close?
So here I'm looking at some data which I have with me here, right? And I'm telling you this not just based on gut instinct, but I'm basing it on some data. US has invested 1.2 billion over the next 5 years, over and above for quantum computing as part of the NQI program. This is over and above the investment that they've done in the past. UK $1.27 billion, India $1.12 billion, European Union 1.13 billion, Netherlands 700 million euros, Germany 650, Russia 790, Canada 1 billion, Australia 4 billion per year. And China is like 10 times that investment, right? And if we're talking about this kind of investment that is happening in the quantum computing space, and we have the right strategy for workforce development, more and more research being enabled in this space, human mind is capable of solving any problem. That's what I believe, right? And we would have cracked it by then. In the next 10 years, we would definitely have cracked this problem, especially with the multiple approaches that are happening. I just saw a presentation from a startup. I went a little deep into the technology. They are thinking of a handheld quantum compute device in the future, right? And that's not going to be there in the next 2 years, maybe not the next 4 years. That's what they're talking about, right? And they're talking about true temperature quantum computer, not even 0 degrees Kelvin. So a lot of different approaches are happening. And there's another thing, if all of these countries continue to do this investment in silos, then maybe we might not reach where we need to reach. But if there is enough collaboration happening amongst the researchers on this world, then I think the collective intelligence of humans on this planet is big enough to solve any problem.
Yeah, I'm with you. I think, look, humanity is not very good at working together, unfortunately, from time to time. But you're right. We have all the tools and the capabilities. So, Simone, I mean, look, blue sky this a bit, 5-10 years, are we actually going to be making some big breakthroughs, do you think?
I mean, look, it's very difficult to give prediction about the future, right? So I will give you my own perspective. Now, I'm a little bit less optimistic than Reena, right? Now, I agree with whatever she said in terms of what the potential is. There are two things that I'm a little bit concerned about. The first thing is the collaboration angle. Now, this technology has the potential to break encryption and has the potential to have very big leaps in what can be used for weapons. Now, those are two things that potentially are definitely against collaboration of major governments, right? Because if you can use this technology to do something that is giving you a competitive advantage as a nation, that's probably not the best thing to basically foster collaboration. The second part of the story is the amount of money which is required for research in this, right? And again, I see the optimist point of Reena, which is a very valid point, right? There is so much money which is pure there that this thing should result in an outbreak and something which is a huge leap in a very short time. Now, the pessimistic way of looking at this is that if you need to have this level of investment to do progress, then you have a huge interest in keeping this progress private because you want to basically get the most out of it. And these two trends for me are trends that can actually lead to a delay in the moment in which there will be a general application of something which is a technology that can be a very big breakthrough in in science, and in whatever we have. So, I mean, my prediction, and I hope I will be wrong, is that in 10 years from now, we will have islands of quantum internets. Yes, they will be probably in the major spenders, communities, and probably still linked to something which is academia or defense. So I don't see that happening. Probably we will need 15 or 20 years to see a more democratic usage of this technology, at least for some specific use cases.
Yeah. Look, I mean, I've heard all of those arguments before, and of course, we're talking about espionage here and the political, geopolitical edge that you want to get over another nation to find out their secrets and what's going on. John Gabriel, I think really, I mean, we are talking about quantum computing, but actually quantum information sciences around communications and, photonics and all these other quantum materials and what have you, there is likely we're also going to see advancements in these areas in parallel to quantum computing, not necessarily because, but in spite of. How do you see the rest of that developing, John Gabriel?
Yes, totally. And I think that's a major point you're raising, that in 10 years, we don't know if RSA is going to be decrypted by a quantum computer. But one thing we know is that we can be well protected. And thanks to quantum key distribution or post-quantum algorithms, we are developing the shield to a future to the future challenge and the future threat. And right now we have quantum-based solutions that are working for communication that could replace or be added to RSA. And one major example is the American Certification Institute, the NIST, is currently developing its new standards of communication that would be unveiled in 2022. And those will be quantum safe, including post-quantum algorithm. So this is the major thing, is that we will be protected against a potential quantum threat on the communication side. And the rise of potential quantum internet will be key for the development of quantum computing, but also quantum communication. And on the quantum sensing part, we will be able also to have developed novel solutions based on innovative physics, and that will unlock some very interesting value in the healthcare industry. For instance, next generation MRI, those are the kind of project we see on the quantum sensing part. And the day-to-day life will be, I believe, will be very different. And if we keep the same innovation pace as we have in the last 4 years, I believe that many good things is going to happen also on the quantum communication and quantum sensing side, because it's less hype than quantum computing, but still key for the industries, for your everyday life, and it's also boiling fields with very innovative projects.
Yeah, I think in summary for that question, I think we all have mixed levels of optimism. One thing we know for sure is people don't play nicely in the playground, and as Simone very clearly said, that although Reena's mentioning loads of capital being played in, are we going to share nicely, and are we going to share innovation? And the point you make, Jean Gabriel, is very important with NIST, because NIST will help us create some structure and some standards. And everyone talks about RSA encryption, which came out of GCHQ in the 50s. But we're talking about different types of cryptography here, NP hard cryptography, such as McLeish, and you've got people like Daniel Bernstein, who is one of the best cryptographers on the planet, working to come up with these standards. So what we're saying in some respects is, although quantum computing is not there yet, and we'll be several years before we get to a machine that is really dangerous, and we're talking 250, 300 qubits. But at that point, we theoretically, of course, can defend ourselves against what's coming down the stream if we're sensible. So, so there's a couple of questions coming from the audience, and it's, as you can imagine, with a panel like this, you get some fairly interesting questions being thrown at us. One gentleman was asking at a very basic level, what makes a quantum computer more efficient and more powerful than a classical computer? Well, I guess the answer is, how long have you got? We could be talking for another hour or so on some of the fundamentals here. What some of the questions are asking is, and it might be worth having another conversation in the future about this, but some of the questions are much more specific to industries, industry solutions. What is going to be the breakthrough in healthcare? What is going to be the things that quantum computing can do to financial services? So, just as a final sort of quick session, let's try and dig into a little bit deeper into some of these industries to see if we can come up with any specifics that we think quantum computing will deliver. And I know, Simone, you touched on this in your paper that you wrote recently, which is an excellent paper. Do you want to touch on any specific aspects of the industry play that quantum computing can deliver?
Yes, to everyone in this room, right? If you look for my name, you can easily find my white paper is basically looking at different industries. Now, it's difficult to give you everything in such a short time. Now, downplaying, I think what a lot of the people are asking is they want something which is very simple to understand. Now, I'm downplaying it, right? I'm super simplifying the topic, but you can think about quantum computing as something which has a level of parallelism which is not even thinkable in a classical computer. So you're basically talking about an hardware for something which is allowing you to do simulation at a very high speed, and it's allowing you to basically do computation for decision making at a very high speed. Now, I'm seriously downplaying what this thing is because I have 30 seconds to cover something that would require a full panel, and probably even more than that. But if you really want to come back with 2 cents out of this, the idea is that you're able to do very fast decision making on very complex decisions, and you are able to basically simulate really complex systems, which can go from weather forecast to understanding how molecules and how viruses are reacting to specific conditions. And as you may expect, the usage of this, it's potentially for whatever industry, and it's touching on the points that I was discussing before.
I think the way I try and explain it, and I'm sure Reena has a slightly different view of this from a physics point of view, but the way I often explain it is that, our only defense against the dark arts of being hacked is actually having very large numbers, which you have to find the integer or the factors of. And in a sense, when people discover that classical computers, because they process, to your point, Simone, serially, they're very slow at actually dealing with very large numbers and large problems. But when you think about quantum computing, it's brute force computing. I call it all at once. There are technically no limitations to solving these challenges. So whilst a classical computer might take hundreds of thousands of years to find the integer of a 600-digit number, a quantum computer can do it in 150, 200 seconds. And there's the magnitude, there's the million-x brute force computing. So for those of you coming up with these questions, imagine applying that level of brute force to your particular industry, your particular challenges and problems, whether it's climate, whether it's solving longevity issues or discovering new materials, new polymers, combinations of drugs working together that can help solve some of the fundamental diseases and viruses that we have today. So hopefully that will give you a bit more of a feel for this quantum computing. One last question to each of you. Those listening in, where do they need to go to learn, or what books and what sites can you recommend, Reena, that enthusiasts who want to become more up to date with quantum computing? Where do they go, in your view? Where can you point them?
So I think there are 2 categories of students in this, right? And we are all students, right? Learning. When I say use the word students, it's more generic. If you just want to learn more about quantum computing at a high level, there are several books which are, like quantum computing for beginners, or you could go to the sites, right? You could go to the popular sites of companies. I can give you mine, and there is documentation there. And similarly, IBM will have it, and Amazon will have it. On the Microsoft side, on the quantum side, you actually have documentation which gives a very easy explanation on how quantum computing happens. Now, if you're from the physics side, right, and you already have a little bit of background, then you can pick up some of the advanced books. I have some of those books here, actually. So there's one, Quantum Computing for Computer Scientists, Introduction to Quantum Mechanics. This is like, I mean, these guys should pay me money. I'm advertising their books, but yeah. There's one called Quantum Computing for Computer Scientists by Nathan S. Yanovsky, and Introduction to Quantum Mechanics by David G. Griffiths. I think these are all good.
A little bit of light reading then, Reena. I mean, what about good old Richard Feynman, and some of the Caltech stuff? I mean, what about you, Jean-Gabriel? When you were learning quantum computing, where was your go-to resource to understand a bit more?
Well, I believe that there are many interesting resources on the web, especially on IBM website. There is also the Unitary Fund for most computer scientists that is providing very interesting features. And I believe that good old Richard Feynman books are perfect, like his lessons at Caltech are very good. And with Quantum Nation, we also founded Le Lab Quantique, which is a non-profit aiming at promoting quantum technology. So we organize often meetups with experts in the field. So you can have a look at our meetups on YouTube and follow Quantum Nation's news. We try to give a glimpse of what is happening in the field, but it's more on a high level and news side.
Fantastic. So Simone, final thought. We've had a good chat. It's a vast subject to cover, a little bit over the hour, but what's your final thought?
Okay, that's a very good question. Now, the reality is that, I think my final thought is everyone here understands the complexity behind something which is basically new and which is completely different, right? Before we were touching on the fact that it's non-deterministic or the fact that it's basically probabilistic, which is something that we are not used to, right? Even people who don't really gauge this are not used to that because we are used to systems which are deterministic because we are humans, right? We like clear answers to clear questions. Now, quantum computing doesn't do that. It's giving you a very probable answer, which is something extremely new for humans to interact with. But we all discuss with our partners, right? So we all actually have something like this in our place. Now, the good thing is that my feeling is that at some point we will make this difficult technology simple to use, and we will make that ready for business users to use. And this is something that has been applied to almost all the technologies that in the 70s or the 60s were considered very complex. We were discussing about books. That there is books I love. Now, my point is, if you want to learn about quantum computing, try to understand what you really need to learn, right? What is really applicable to what you need, because if not, you will just lose yourself there.
And Reena, what's your final thought? Come on, it's you have lots of thoughts, I know. How do you want to leave the audience thinking?
So I would agree. I think if people have come to this session, then they have some interest in quantum computing. If you are a general enthusiast, don't refer to the books that I'm talking about. I've shared some books. Those are more if you want to go deeper into the maths of it. Then you can, I think the recommendation would be read up on the internet, look for, the Microsoft site would still be useful because it will help you give some generic information as well. I think that, we are at early stages of the quantum revolution, so to say. So there's a level of abstraction that is building up. As we move forward, everybody doesn't need to know quantum computing at that depth. There will be users, as Simon pointed out earlier, right? And those users need to understand, they will have programming interfaces available to them. They need to be able to use that and understand how to apply that to certain use cases. That will also require some amount of studying up to understand how quantum works at a very, very abstracted level. You don't have to go deeper into the mathematics of it. But if you're interested in the field and you want to do deeper work, let's say when the classical computing was starting, there were people who wanted to work on the network layers and the operating system. If you're one of those people, then you should think about moving your career in the academic, picking up more electives in that direction, and getting more deeper insights into quantum information science and the various topics that are available today in colleges with relevance to quantum. So I think there's a place for everybody as we move forward. And I think one of the challenges I see is everybody thinks that they have to study the same stuff. You have to go deeper, you have to understand the maths. No, really not. Right? That's for the people who want to do deep research. Yeah.
And Jean-Gabriel, final thought from you?
Well, I think that we always speak about the long-term application of quantum computers, but one major message I wanted to share today that there are short-term opportunities currently being built, and it's not too late. And also, you have to move right now in order to be part of the industry of the future, because there are barriers at the entry. And I think that's a very good thing that the Saudian government is currently understanding what is happening and is trying to move forward in this field, because it's the moment where you can have partnerships and collaboration with a lot of entities in order to help you put a foot forward and be able to just develop a quantum sovereignty.
Yeah, look, I think it's a very good summary, and I'd like to thank all of you for your deep thoughts and insights. For the audience listening, quantum computing, you haven't missed the boat. There's lots of opportunity. It's early days, and from my point of view, I think that when I discovered this journey as a computer scientist, as Simone said, it's very hard to unlearn in a sense. And when you go into the realms of quantum, it's very different. Even Einstein struggled with some of the principles of quantum computing and how these little subatomic particles create relationships which unlock all this enormous power. So a bit of basic physics doesn't go amiss to understand. Go back to school, reread some of those classes. I used to find physics enormously boring when I was younger at school, but if I'd paid attention, maybe I would have known more. So do some basic reading, some background reading. It's all good. It's all there. I'd like to thank very much ThinkTech for organising this, and also the Saudi Ministry of Communications and Information Technology. I'm sure all the panelists would like to thank you all for listening and paying attention. And if any of you want to follow up and ask us questions, I'm sure we'll be available to answer your questions. So on that note, thank you very much, everybody. Good evening, good afternoon, good morning, depending where you are. And we'll see you all again very soon.
Thank you.
Thank you very much, Nick.